Welcome back to linear algebra. In this video, I want to look at constructing subspaces of generalized or abstract vector spaces. We've talked about subspaces in the past. Remember that a subspace of a vector space is any new vector space which is a subset of the original vector space and uses the same operations for vector addition and scalar multiplication. There's not really a lot new in the theory that we're going to be looking at here, although we are going to be able to take a bit of a closer look at some things. Mostly this is an excuse to look at how some of the structures of abstract vector spaces come to be. Let me get my head out of the way and let's get started. All right, so just what I said before, but I'll write that down. Let V be any vector space, and a subspace of V is any set W, so that W is a subset of V, W is a vector space, and the vector space W uses the same definition of vector addition and scalar multiplication as V. So if we let V be any vector space, and we let W be a subset of V, we can conclude that W is a vector space using the same definition for vector addition and for scalar multiplication as V, if and only if, first, W is non-empty, and second, W is closed under linear combinations. We had this definition, or this theorem, when we were talking about subspaces of Euclidean vector spaces. So this isn't anything new. Although I do want to emphasize here, W is non-empty. When we looked at this before, the theorem specifically said that the zero vector had to be in W. And in practice, that's usually the way we deal with it. Usually, finding the zero vector is the easiest thing to find. And if we can show that the zero vector is in our set, then we're good to go. But technically speaking, you can actually do this with any vector. It doesn't have to be the zero vector because of the property of closed under linear combinations. Because if you have any two vectors, u1 and u2 in W, and you have that W is closed under linear combinations, then because V is a vector space, u1 and u2 are in V, and because these use the same definition of vector addition and scalar multiplication as V, we can evaluate 0 times u1 plus 0 times u2 in vector space V. We can use the fact that in vector space V, this has to be the 0 vector, and then use the fact that W is closed to conclude that the 0 vector is in fact in W, no matter which vectors we started with. That's not exactly a conclusive proof. That only gave us, well, I guess one of the properties, but if you go back and you look at all of the properties of vector spaces, closed under vector addition. Well, if it's closed under linear combinations, it has to be closed under vector addition. Just choose the constants to be 1. The commutative and associative properties, the definitions of these vectors haven't changed, or the definition of vector addition hasn't changed from V, and V satisfied these properties, so we're good to go. 0 vector, we've established that. Inverses, well, we're closed under linear combinations. So -1 times V we showed in the vector space is the opposite of V, and by closure it must be in W as well. Closed under scalar multiplication. Again, scalar multiplication is a special case of linear combinations. It's a linear combination of one vector. All of the properties of how scalar multiplication distributes. Again, we're building on the definition of a vector space, so we've already established these rules for scalar multiplication. Distribution across vectors, distribution across scalars, association with scalar multiplication, and that nice property with the number 1. So all of those things get inherited from the original vector space, and all we really have to care about are those 3 specific properties. The 0 vector is in there, the closure under vector addition, and the closure under scalar multiplication. So from these 2 properties, we can get all 3 of those without too much work, and checking 2 things is a little bit easier than checking 3 things. So as an example, let's consider this set W. It's the set of quadratic polynomials, ax squared plus bx plus c, and we're specifically going to insist that a plus b is equal to c. And our instructions here are to show that this is a subset of P2, which I think we can establish without writing anything down, and that it is a vector space. If it is a subset of P2, then we're really looking for a subspace. Well, to show something is a subspace, the first thing you have to show is that it is not empty. We have to find a vector inside of this vector space. And as I mentioned, the 0 vector is often the easiest one to deal with. In this case, if we pick A, B, and C, all equal to 0, Well, 0 plus 0 is equal to 0, so it satisfies the definition of W. And we have an element of W. Well, that's a problem. I ran out of letters. I should think ahead sometimes. All right, P of x is going to be ax squared plus bx plus c, and Q of x is going to be dx squared plus ex plus f. And that way I'm not running into extra letters, f showing up multiple times. That was annoying. And I want these both to be in W. So C equals A plus B, and F equals D plus E. And then I need a couple of real numbers. I'll call them K and L. And with that, I can take my linear combination. K times P of x plus L times Q of x is K times ax squared plus bx plus c plus L times dx squared plus ex plus f. Then, substituting in, I know that C is A plus B. I know that F is D plus E. And continuing from here, I can distribute. And I can use the commutative and associative properties of real numbers to rearrange these things so that I have Ka plus Ld all times x squared. I have Kb times Le all times x. And I have constants, which I'm going to group as Ka plus Ld plus Kb plus Le. And if you notice, this absolutely is in the form of something in W. W is not empty. The zero vector at the very least is in this set. And in fact, there are infinitely many polynomials in the set, but at least one is all I care about. And it is closed under linear combinations. If I take a linear combination of two polynomials in the set, I get a result that I can show is another polynomial in the set. The coefficient on x squared plus the coefficient on x is the same thing as the constant term. Since I showed this arbitrarily, it must be true for every linear combination, and that's what it takes to show that we have a subspace. Let's take any arbitrary vector space. Let's take a set of a finite number of vectors in that vector space. The span of S, which you can write literally as span of S, or you can denote using angle brackets. Depending on which source you are reading, one or the other is more popular. And the span of the set is the set of all the linear combinations, C1U1 plus C2U2 all the way down to CKUK. And as we showed with the Euclidean vector spaces, in an abstract vector space, the span of a set must be a subspace of the original vector space. You can take a linear combination um, and set all the constants equal to 0 to get the 0 vector. And if you take a linear combination of linear combinations, it's a linear combination of the thing you started with. All right. I'm not going to write that out just for the sake of time and effort, but you can verify that for yourself by literally just writing out a linear combination of two things in this set. The notation gets a little bit headache inducing and cross-eye, so I don't think it's interesting, but it is something we can do. So for example, if I take a set of a couple of vectors, x, x plus 1, and x squared plus 1 as a subset of P2, then the span of S is the set of all vectors C1 times x plus C2 times x plus 1 plus C3 times x squared plus 1. I claim that this particular choice actually gave me the set of P2, the set of all quadratic polynomials. To show that two sets are equal to each other, we use the process of subset inclusion. Right. From our theorem, the span of this set is a subset of P2. Every vector in the set is a vector in P2, and since P2 is closed under linear combinations, the span is also closed under linear combinations. Or, since P2 is closed under linear combinations and the span of S is a bunch of linear combinations of things in P2, then they all have to be in P2 and we get that subset relationship. So what we want to show is the other direction. Pick ax squared plus bx plus c in the set P2, and we want to show that this is also in the span of S. If it is, then that means that ax squared plus bx plus c is equal to some constant. Well, I've already used c here, so I don't want to use c again. I'll switch to k's. K1 times x plus k2 times x plus 1 plus k3 times x squared plus 1. And if I distribute on the right-hand side, I get k3 x squared plus k2x, I'm sorry, k1 plus k2 x plus k2 plus k3. In order for two polynomials to be equal, it must be the case that corresponding coefficients are equal, which means in this case that A is equal to K3, B is equal to K1 plus K2, and C is equal to K2 plus K3. A, B, and C are fixed. We picked a particular polynomial in P2. K1, K2, and K3 are our variables. We want to know if there are values that satisfy this equation. We're not certain that they are going to be there. But as linear systems go, this is a little bit abstract because there's no numbers, but the process is actually really easy. From the first equation, we get that K3 is A. Plugging that into the third equation, we get that K2 is C minus A. And plugging that into the second equation, we get that K1 is B minus C minus A. Right? Again, just the first equation, plug that value into the third equation, rearrange, solve for K2. Plug that response into the second equation, rearrange, solve for K1. And we see here that there must be K1, K2, and K3. So we can write every single polynomial, every single quadratic polynomial as a linear combination of x, x plus 1, and x squared plus 1. That means that P2 is a subset of the span of S and the only way for S to be a subset of P2 and P2 to also be a subset of S is for P2 and S to actually be the same set. So we could write the set of quadratic polynomials as the span of these three polynomials. I'm not sure what value that has, but it is something we can do, and that's what really matters. I would like you to take a look at this set. W is the set of all vectors, some constant a1 times x cubed, plus some constant a2 times x squared, plus some constant a3 times x. And I want you to show that this is a subspace of the vector space of fourth degree polynomials P4. There is an easy way and a hard way to go about this based on the things we've talked about in this video. One of them requires a lot of setup and not much grunt work. The other one requires very little setup and a lot of computational complexity. I'm not sure which one you'll call the easy way or the hard way, but as long as you find one of them, I'm very happy. Take a couple of minutes, see what you can do with that, and I'll see you in the next video.